Hey everyone, welcome to the Explainer. Today, we're jumping straight into something absolutely fascinating, advanced sentiment analytics. Specifically, we're going to look at how data science and machine learning are literally decoding human emotion. I mean, we interact with text data constantly, right? Reviews, social media, a mountain of emails. But how do we actually teach a machine to understand the feeling behind those words? Well, let's get right into it.
So think about this for a second. How exactly does a computer understand sarcasm? I mean, let's be real. Half the time we humans struggle to catch it in a quick text message. Human language is incredibly complex. If I say something like, "Oh, brilliant, another flat tire," you and I instantly know I am absolutely not happy about that flat tire. But to a machine, the word brilliant usually means something highly positive. So interpreting that tone, that context, it's really one of the biggest challenges in data science right now. Okay, let's dive into this by looking at how we used to solve this problem compared to the powerhouse methods we use today. On the left, we've got the old school method, the lexicon-based approach. This is essentially a giant, incredibly rigid dictionary where someone literally sat down and manually assigned a score to words. Say, a +1 for good and a -1 for bad. It's completely rule-based. Now on the right is the machine learning approach. Here, instead of relying on a fixed dictionary, the computer is actually learning patterns directly from the data itself, making it highly adaptable to real-world context.
And honestly, the old lexicon approach, it's exactly why we desperately needed an upgrade. A fixed dictionary treats every single word independently. It completely fails to capture meaning in context, it completely misses the mark on that sarcasm we just talked about, and it has a really limited vocabulary that is an absolute nightmare to update manually. Machine learning solves this because it learns from huge data sets. It catches complex language, negation, slang, even emojis. It actually adapts to real-world complexity, which gives us way better accuracy.
So, here's our roadmap for this explainer. We're going to cover decoding human emotion, the machine learning pipeline, choosing the right algorithm, training and testing strategies, and finally, evaluating model performance. All right, let's kick things off with part 1, decoding human emotion through sentiment classification. The ultimate goal here is pretty straightforward. We want to automatically assign a sentiment label to a piece of text. Think of it like sorting text into emotional buckets. Take IMDb movie reviews, for example. We've got raw text like amazing movie, great acting, and story. The machine learning classifier processes that text and drops it straight into a positive bucket. Worst movie ever goes to the negative bucket, and it was okay lands in neutral. We want to automate this whole process so we can generate insights at a massive scale without having to sit there reading millions of reviews ourselves.
Moving right along to section 2, the machine learning pipeline. This is all about going from raw text to actual insights.
Because, a computer can't just sit down and read an English sentence like we do. We have to transform it. Step 1 is collecting that raw text. Step 2 is absolutely critical, preprocessing. This is where we clean up the noise, we make everything lowercase, we strip out punctuation, and we filter out common stop words like and or the that just don't carry any real emotional weight. Step 3 is extracting features. Basically, this means turning those cleaned up words into numbers, translating human language into a format that computers' math can actually digest. Then step 4 is training our model on those numbers. And finally, step 5 is making predictions and evaluating how well we did.
And this brilliantly illustrates what that step-by-step pipeline actually looks like under the hood in a data mining software workspace. You can trace it from left to right. We load the file, convert it into a text corpus, pre-process it to strip out all that noise we mentioned, and turn it into numerical features using techniques like bag of words or TF-IDF, which, by the way, is just a fancy way to weigh how important specific words are to a document. Then, we feed those numbers right into our machine learning models. You can see naive Bayes, logistic regression, and random forest lined up there, before finally pushing it all into our evaluation tools on the far right.
Which brings us to section 3, choosing the right algorithm, or finding the best model for the job.
You can kind of think of these algorithms as different types of digital brains. There's no magic, one-size-fits-all solution here. You've got to pick the right tool for the job. Naive Bayes, for instance, is based on probability. Its massive superpower is that it's insanely fast and simple, making it a fantastic baseline to start your project with. Logistic regression is great for straightforward binary classification and is highly interpretable. But if you need something more robust that handles really complex nonlinear patterns, you might step up to a random forest, which uses a whole ensemble of decision trees. Or you might deploy a support vector machine, an SVM, which is incredibly powerful when you're dealing with thousands of unique words across massive data sets.
Next up is section 4, training and testing strategies, focusing on train and test splits. Let's move to and see how this builds our model's reliability. The absolute go-to technique for a quick, general-purpose check is the holdout split. Basically, we take all our data and chop it up. We use 80% of our data, the train set, to teach the algorithm what positive and negative language looks like. But we intentionally hide the remaining 20%, the test set. Once the model is fully trained, we throw this unseen 20% at it to see how accurately it predicts the sentiment, completely blind, without knowing the answers in advance.
And finally, Section 5, evaluating model performance using metrics and visualization.
Now, what's really interesting about this slide is how it demystifies the whole process of finding our model's mistakes. Enter the confusion matrix. It literally maps out the actual ground truth against what our model predicted. Up in the top left, we have true positives. The model predicted it was positive, and yep, it actually was. Bottom right, true negatives. It correctly spotted the negatives. But those other two boxes? That's where the trouble is. You've got false positives, where the model raised a false alarm, and false negatives, where it completely missed the target.
From that matrix, we can pull out our key evaluation metrics. Accuracy is exactly what it sounds like, the overall correctness of the model. But accuracy isn't everything. Precision measures the quality of our positive predictions, meaning of the ones we called positive, how many actually were. Recall measures how many of the real positives we successfully found. So, the crucial point is that depending on your real-world situation, a false positive might be incredibly costly. Like, imagine flagging your boss's important email as spam. You definitely want high precision there. On the flip side, missing a true case might be disastrous in other contexts, meaning you'd want to optimize for high recall. The F1 score elegantly gives us a solid, harmonic balance of both.
Finally, we've got the ROC curve. This basically evaluates our model across all kinds of different probability thresholds. It graphically plots our true positive rate against our false positive rate. When you're looking at one of these curves, you want that line to bow as close to the top left corner as possible. That top left corner, that's the absolute holy grail of model performance. It means your model is identifying almost all the true positives while generating almost zero false alarms. The area under this curve, the AUC, quantifies all of this performance into a single number. The closer it is to 1.0, the better your AI is performing.
To wrap things up, the core takeaway from this explainer is just the incredible leap forward we've taken in data science. By shifting away from rigid, manually updated dictionaries and truly embracing the machine learning pipeline, we've built adaptable AI that actually learns from data. We collect, we pre-process, we extract features, and we train powerful models that can decode the true context, the nuance, and yes, even the sarcasm of human language. Because by structuring our data and rigorously evaluating our models using confusion matrices and ROC curves, we can actually trust computers to read human emotions at scale. So I'm going to leave you with this. Now that your computer can effectively read emotions, what hidden patterns will you uncover in your own data? Thanks so much for tuning in to this explainer, and happy analyzing.